All right. Thanks for the kind introduction. Yeah, so adding this to the agenda last minute here, doing a quick, just couple minute introduction or teaser on some of the material that we'll be covering in the tutorial on Qiskit this afternoon. Wanted to make sure everybody's just sort of level set on just the very, very basics of quantum circuits, so everybody's on the same page for those tutorials. So for some people, fall asleep, this will be terribly boring. For some people, this will be helpful, but in either case, it'll be quick. So very brief review. The first slide on any presentation on quantum circuits, of course, is going to be about classical circuits, right? Our nearest and dearest analog. So with classical circuits, with a Boolean logic circuit, you have a couple different gate options. A lot of you have probably seen these kinds of diagrams before. You have AND gates, OR gates. This is the basis of all the Boolean logic that we do in regular computer science, right? And so you can chain these together and have little logical circuits that compute, A and B or not B and things like this. So this is sort of what's existed for 50 to 100 years. Quantum states and gates here. Again, notationally, I think we did a show of hands the other day saying everybody was completely comfortable with the Brockett notation, so this should not be a surprise, which is good. But you have a state of your qubit decomposed into two coefficients, a linear combination of these two different basis states. Alpha and beta are the probability amplitudes, so these are complex numbers, and so the norm squared of alpha plus norm squared of beta is equal to 1. And these coefficients, the probability amplitudes on your qubit, are isomorphic to a vector in C2. And so this is sort of the representation we use. So I'll say this again when we do the tutorial this afternoon, but the language of quantum mechanics and quantum computing, you all know this by now after a couple days of awesome talks. The languages of quantum computing are linear algebra, and I'll add Python to that this afternoon. But linear algebra is our lingua franca here, and if we want to transform one vector, a state of our quantum system, into another state, what are we going to do? Change one vector into another, we'll use matrices, right? And so the key point here, a single qubit quantum gate is a 2x2 complex matrix, and it'll be unitary as well. There's a bunch of physics implications of that operator being unitary. It's reversible, information preserving, however you want to think about it. So again, quantum computing, the mathematics is sort of as nice as you could hope for in a lot of ways. So quick tour of some common single qubit gates you see. A lot of these have analogs to classical logical gates, which I think is kind of important to keep in mind. So for example, if you have the X gate here, this is sort of analogous to like a classical NOT gate. It looks like this friendly little matrix here. So if you, it'll swap the probability amplitudes in front of each of these two basis states. In addition to manipulating just the magnitudes of the probability amplitudes, you can also adjust their phase, their sign, or their relative phases to each other. So for example, the Z gate, which is also called the phase flip gate, does exactly that. So you'll have the same probability of measuring 0 or 1 here, but with these quantum states, you have this extra degree of freedom here, which is the phase of each of these coefficients. A few other ones, Hadamard gate. Hadamard gate is a super important gate because it allows you to take a state, for example, 1, 0 or 0, 1, and basically can create a superposition of those two states with equal probabilities. So zooming right along in the couple minutes we have, you can also have quantum gates that operate on multiple qubits simultaneously. The most famous of those examples is the controlled NOT gate, or the C-NOT gate. This looks like almost an identity matrix. It looks like a block diagonal matrix, so you've got a block of the identity and then a block of the X gate or the swap gate here. And the effect of this is, one way to interpret this is that the first qubit, if you write out your qubits in the standard sort of computational basis here, if your first qubit is 0, then the C-NOT gate will not change the value of the second qubit, and if your first qubit is equal to 1, then the value of the second qubit gets flipped. And you can prove that, just work out the linear algebra on your own during the break or something. But essentially, this first qubit acts as a control which is why it's called the control NOT gate. So depending on the value of your first qubit, the second qubit will get flipped or not, is one sort of interpretation. So zooming along quickly here, that's sort of a quick overview of quantum gates and their matrix representations. A quantum circuit then is just a combination of all these gates. So typically you draw circuit diagrams like this or like this. They're drawn from left to right. You sort of ignore any identity gates, so you only need to draw gates where they're actually having an effect on a particular qubit. And sometimes, we'll see this in the tutorial later today, you'll see some vertical lines or some dashed lines here that are just logical separators between different parts of what your circuit is doing. One other thing, you'll see a lot of these measurement symbols added on to the circuits towards the end, because a lot of the time you actually want to measure the result of what your circuit is doing, right? And just one note that a quantum algorithm, just for being sort of precise about terminology here, an algorithm may involve evaluating a particular circuit a bunch of times. So you might need to sample a circuit 1,000 times to get some probabilistic answer, or maybe you're taking the output from one run of your circuit and feeding that back in an iterative fashion, things like that. So it's a small differentiation there. Otherwise, the only other note is for sort of the C0 gate. There's usually this sort of notation where you have sort of like a hollow circle for your control qubit, and then a little circle with a plus in it for your target qubit. Okay, so last sort of point I wanted to make here is that if you have a quantum circuit, if you have a diagram like that, it's going to look like that sort of linear sequence of gates and matrices. And so if each quantum gate is a matrix, and these things are operating one at a time, then a whole quantum circuit also looks like one large unitary U, right? You can just take all of those gates and multiply them all together. Take the matrix representations of those gates, multiply all those together, and you get one giant unitary matrix that describes the action of your entire circuit on the initial state of your quantum system. And so just a couple quick interesting points, which I think are relevant for mathematicians to think about. What if all you're given is U, somebody gives you this big matrix U, and you want to try to build a quantum circuit out of that, right? Somebody says, build me a circuit that does this. Well, it turns out that's sort of a hard problem, right? How do you factor a unitary matrix U, just arbitrary thing, into a set of those basic gates? There's a really famous result in quantum computing, the Solovay-Kitaev theorem. It's sort of a constructive theorem, so the way they prove the theorem is by giving an algorithm that demonstrates this. And so it says that with a universal gate set, which is just like 7, somebody can correct me, but 7 or 8 or 4, some small number of gates, like an X gate and a Hadamard gate and a couple of these things, that's enough to be able to approximate any unitary, any circuit arbitrarily well, as you let the number of gates increase. This is like a limit type of thing. You might need an arbitrary number of gates to approximate a circuit arbitrarily well, but in principle you can do it. And this is an active mathematical, theoretical CS research area. So there are a bunch of newer things that have come out since Solovay-Kitaev that have improved upon sort of the theoretical bounds and also the practical implementation and speed. So an area to look at if that's sort of interest. And I'll leave you with one idea, and then I'll conclude. And let's see, what if we're only given example input-output pairs? So to make the problem even harder, what if we're not even given the unitary matrix U that's describing our circuit? What if we're just given a collection of input states and desired output states? You tell me what you want this quantum algorithm to do, but you have no idea what the quantum algorithm or the circuit looks like. This is the next level of difficulty. Can you still figure out what the quantum circuit or the quantum algorithm should be? It turns out the answer is yes. You can derive the matrix U, and then using those algorithms I mentioned on the last slide, factor that into a circuit diagram. So I have a preprint you can read, or find me in the break and ask questions. But that's sort of the beauty of quantum circuits and quantum algorithms. I would argue the mathematics and sort of the formalism of this is even nicer than classical algorithms. ChatGPT doesn't really work so well to give me classical algorithms as well as I'd like. But yeah, I will go ahead and leave it there. and I look forward to seeing everybody later this afternoon at the tutorial. Thank you.